Hey everyone, welcome to This Explainer. Today, we're diving into a genuinely historic piece of research. I mean, if you've ever found yourself wondering how modern AI got so unbelievably good at understanding and generating human language, well, you're looking at ground zero. We are unpacking the 2018 OpenAI paper titled Improving Language Understanding by Generative Pre-training. Simply put, this is the paper that laid the very foundation for modern generative AI and completely changed the game for natural language processing. But to really grasp why this was such a massive breakthrough, we've got to start with a huge fundamental problem. Ask yourself, how do you teach a machine to actually understand language when you literally do not have the time to label the data? It was the ultimate catch-22 of early machine learning. You know, you want your AI to be incredibly smart, but teaching it without endless, painstaking human handholding just seemed almost impossible.
Okay, so let's dive into this. Here's our roadmap for today. First, we'll examine the labeled data bottleneck. Then we'll look at the two-stage solution, followed by transforming the architecture. After that, we'll see exactly how they smashed the benchmarks. And finally, we'll wrap up with the zero-shot revelation.
All right, starting right off with Section 1, the labeled data bottleneck, or the problem of scarce labeled data. So picture this. You've got the internet, this abundant, virtually infinite ocean of raw, unorganized text. But on the flip side, you have incredibly scarce labeled data. Prior to this paper, most deep learning methods required massive amounts of manually labeled data to learn a specific task. Think about it. If you wanted an AI to detect sentiment, humans literally had to sit down and manually tag thousands upon thousands of sentences as either positive or negative.
And here's the real kicker. Manual annotation is just ridiculously time-consuming and prohibitively expensive. If we rely purely on supervised learning, where humans basically have to provide the answer key for every single training example, our AI is always going to be bottlenecked by how fast we can label that data. We would simply never ever have enough labeled data to teach AI the broad, nuanced complexities of human language.
Which brings us to Section 2, the two-stage solution. This was a totally new training paradigm.
The OpenAI team realized they could completely sidestep this bottleneck with an elegant two-step process. Think of it kind of like training a world-class student. Step 1 is unsupervised pre-training. This is like the student just going to the library and reading millions of books to absorb how the world works, how grammar functions, how concepts link together. No teacher required, just raw reading. Then, Step 2 is supervised fine-tuning. This is where the student takes specific practice exams to specialize in a subject, say biology or history. Because they already know how to read and reason from Step 1, they need way less supervision in Step 2 to actually master the task.
Now, for that vital first step, the unsupervised reading phase, they basically handed the model a library card to the book's corpus dataset. And this wasn't just random fragmented internet chatter. It was over 7,000 unique, unpublished books spanning genres like adventure, fantasy, romance. Why books, you ask? Because they contain really long, contiguous stretches of text. This uniquely forced the generative model to learn how to track long-range information. It had to remember a character or a plot point from paragraphs or even whole pages ago.
Moving right along to Section 3, transforming the architecture, specifically building a structured memory.
So instead of using the recurrent neural networks, or LSTMs, that were the industry standard at the time, they went with a 12-layer, decoder-only transformer. This architecture stacks masked, multi-self-attention layers. What that actually means is it allows the model to look at a whole sequence of words and mathematically weigh the importance of every single word against every other word in that sequence, rather than processing them strictly one by one.
The researchers actually hit the nail on the head in the paper. They wrote, "This model choice provides us with a more structured memory for handling long-term dependencies in text." And honestly, that's the secret sauce right there. By using the transformer, the model wasn't just predicting the next word based on the previous 3 words. It was pulling rich context from the entire passage. This resulted in a far more robust understanding of language that transferred beautifully across all sorts of diverse tasks.
Now, what's really brilliant here is how they handled Step 2. The fine-tuning. Traditionally, if you wanted an AI to do, say, multiple-choice questions, you had to build a clunky custom architecture just for that one thing. The OpenAI team completely bypassed this by using input transformations. They used simple start, extract, and delimiter tokens to basically format the text into a single, contiguous sequence. So you get minimal structural changes, but massive, massive versatility.
All right, Section 4, smashing the benchmarks. Let's look at the new state-of-the-art.
9. Yep, that's the magic number. This single, general-purpose, completely task-agnostic model literally crushed the absolute state-of-the-art records in 9 out of the 12 natural language understanding tasks they studied. It didn't just casually compete, it completely dominated models that had been specifically and painstakingly handcrafted for those exact individual tasks.
And we're not talking about minor tweaks here. These data gains were massive. On the Stories Close test, which measures common sense reasoning, it hit an 8.9% absolute improvement. On the RACE dataset, which is made up of really tough middle and high school reading comprehension exams, it jumped by 5.7%. For the GLUE multitask benchmark, up 5.5%. And on multi-NLI for textual entailment, up 1.5%. Simply by reading a huge library of books totally unsupervised and then doing just a little bit of fine-tuning, it thoroughly decimated specialized architectures.
Finally, Section 5, the zero-shot revelation, learning without labels.
Look at how this builds. Bringing over more layers from the pre-trained model to a specific task consistently boosted accuracy, which proved that every single layer of that transformer was learning genuinely useful functionality. But the real jaw-dropper? That's the model's zero-shot performance. They basically asked the model to do tasks like sentiment analysis or question answering without giving it any supervised fine-tuning at all. And miraculously, as the model read more raw text during pre-training, its ability to perform these specific tasks steadily climbed.
So, what's the big takeaway here? It's absolutely profound. The model was accidentally learning how to do specialized tasks just by trying to predict the next word in a book. Generative pre-training natively learns task-relevant functionality. It actually acquires deep linguistic knowledge, like knowing if a sentence is positive or negative, without any human ever explicitly training it to do so. The unsupervised learning was doing all the heavy lifting.
So, this 2018 paper didn't just fix a bottleneck, it blew the doors completely off the hinges and opened an entirely new paradigm. Which leaves us with one massive, provocative question to think about. If unsupervised learning using a transformer can unlock this much potential from just 7,000 unpublished books, what happens when we scale the data, the computing power, and the parameters even further? Well, looking at the AI landscape today, I think it's safe to say we're all witnessing the answer. Thank you so much for joining me for this explainer, and keep learning.